All right. We just talked about sound. We're talking about sound hits the surface. It can either be transmitted. It could go ahead and go through, for example, the sound hits the wall. Some of it could keep on going through the wall. That would be transmitted. Okay. It could be absorbed by the surface. Usually, if you have a lot of airspace is solid, airspace is solid, it loses more sound as it changes from one medium to the next. And so eventually it's more likely to absorb the sound. Okay, or it could be reflected or bounce off. Now, if something bounces off, the incoming sound wave is called the incident. And we'll talk about these same phrases when we get to other ways to reflect particularly light. This is the incoming sound wave. Okay, and then you have the one where it's bouncing out over here. That is the reflected ray. All right. Which is the outgoing, or the one that bounces off. All right. Outgoing. All right. So it's going outgoing. Now, if we were to put something perpendicular to the surface, this is called the normal. Okay. The normal is just a line that would be perpendicular to the surface, comes in and bounces off. Now, the angle between the incident ray and the normal, and the angle between the reflecting ray and the normal, you will notice, are equal. All right, they're exactly the same, and so those should have exactly the same angle from here to here that you have from here to here. So that's just basically one of the rules of reflected rays is that the angle, I'm just going to use that symbol for angle, of incidence, okay, is equal to the angle of reflection. Okay, and so angle of incidence is just the angle between the incoming ray or incident ray and the normal, so right there, and the reflected ray here, and that will always reflect to where these are equal. Okay, and that will be true when we talk about other ways, including light rays and things like that. One of the common uses that we make of reflected sound, besides Doppler, which we'll talk about later, is ultrasound sonography. Okay, ultrasound. Ultra then means that these are wavelengths that have higher frequencies than we can hear. Okay, sonography, sonic, boom, so forth, has a sound. So sonography, graphy means to make a picture, drawing, or writing. In this case, a picture. So we're using high frequency sound that we cannot hear, ultrasound, to make a sound picture of the inside tissue inside of, most often we think of babies. Now, not just in babies, that's probably the most common place that people have encountered this, but it's also very important for many other organs. It doesn't always give the best picture, but if it will tell us enough, we can do this. Ultrasound is cheap. Fairly inexpensive to do, costs a lot, like MRIs, and X-rays, and things like that. Also, it does not expose you to any kind of radiation or anything. It's a sound wave; they do no damage to your tissue. So, in that sense, that's a very good deal. Many other kinds, MRIs are okay, but X-rays and gamma rays are used in all the other radiation techniques and so forth could do damage and actually cause cancer and things like that. So you don't want to be exposed to any more than that. You have to, so a lot of times they'll do an ultrasound. If that will show what they need to see, then they're good. They can just move on. They don't have to do any other kind of radiation treatment or radiation technique to look at you, but sometimes they will have to do that. So it's a good way to check if it's possible. Other thing about ultrasound and sound waves that are reflected, a lot of times are used by animals, in particular dolphins, bats. Dolphins use this to navigate. They also seem to use it to talk to each other. They use sound waves or things to talk to each other. I've had dolphins that are in a maze. They go through the maze, and they hear them making noises with the other dolphins, and then they put dolphins who've never been in the maze, and boom, they go right through the maze. So apparently they can use it to communicate. Bats, of course, will send out ultrasound sound waves. It hits insects, bounces back, and based on how it comes back, we'll talk more about the Doppler effect. They can tell where the insect is and go catch it and eat it, and that's one less blood-sucking mosquito we have to worry about, so that's a good thing. We like bats. Bats are a good thing. So that's one way of applying this type of technology. All right, another characteristic about sound waves, other than reflection, is a similar word, refraction. Okay, refraction. Okay, and refraction has to do with when a sound wave doesn't bounce, but rather when it bends, because some of the wave is moving faster than other parts of the wave. Okay, and it can move for different. One can move faster because of the medium. Okay, if one is going through air, if it's going through air and it hits water, okay, sound waves when they hit water, which is a liquid, will speed up. Well, if this part of the wave starts speeding up and this part's still going about the same speed, they're going to start bending. Okay, and so it's going to bend the wave, and as it comes here, if this part speeds up, it's going to bend. Sorry, I messed this part up, but it's going to bend, and it's going to start going that direction. So it was coming here, but now it's sped up. This end sped up first, so that the bottom end here sped up first. That's going to tilt it that direction. Okay, so it's not going to go off this direction. Well, it's coming in kind of like this. Now it's going off that direction. Okay, so that's an example of refraction at different mediums. It can also be because of temperature. Okay, if you have different temperatures, remember once again, sound waves are going to travel faster in warmer air. Okay, and so if the air is warmer, they're going to move faster. So if they hit warm air, they'll move faster. An example of that right here is, okay, trumpet players playing it here. There's cool air up here, but the ground is heating up, so it heats up the air here, and this air is warmer. So once again, when it comes here, as the sound waves are coming, sorry, let me switch over, okay. Sound waves are coming here. As this air warms up, the bottom starts going faster, and you see how they start tilting up, and it bends them, okay. And they may actually, this person over here may not be able to hear it very well because the sound waves are bending and going over their head. Or if they hear it, they may not hear as good a quality of sound. Okay. On the other hand, if you had cooler air underneath and warmer air up on top, okay, maybe in the morning the air appears warmer than the air on the ground, for whatever reason. Okay. Same thing. The top of the wave now is going to start moving faster, and so if anything, it starts curving down, and the dog in this case is going to hear a full range of the sound and much louder. Okay, so refraction is just caused by bending. We'll talk about this when we talk about light in particular. It's a very important thing. We talk about focusing light, but it's also true of sound waves. Yep. Now, sound waves can also cause other objects to start moving, and there are several different ways you could do this. If you had a table, oops, we're drawing a table. Okay, let's just say you have a table or a table leg. A very simple table. Okay, and you are going to have if you have a tuning fork that you hit, tuning forks are kind of U-shaped thingies here with little pieces of metal that vibrate at a particular frequency. So if I hit this and it starts vibrating, it sends out vibrations. But if it also sends out vibrations down through the metal this way, and if I put it on top of the table, it will cause the table to start vibrating. It'll start vibrating and sending off vibrations off in the same frequency. Okay, and so the table is vibrating at the same frequency as the fork. So we say the fork is forcing, the tuning fork is forcing, not a regular fork, but a tuning fork is forcing the table to vibrate at the same frequency. So this is called a forced vibration. Okay, in other words, the table has no choice about the frequency. It's going to rotate at the same frequency or vibrate at the same frequency as the fork. Examples of this would be like machinery. If the motor of your car starts to vibrate, it's going to cause the frame and the rest of the car to vibrate at that same frequency. So that would be force. Sometimes a fan gets out of alignment or has a bad ball bearing, it begins to shake. And so the rest of the fan shakes at the same frequency. That would be forced. In the air inside a musical instrument, like a saxophone or whatever else, it starts to vibrate, and it forces the actual body or the metal or wood that the instrument's made out of to vibrate at that same frequency. Okay, so that is what we call a forced vibration. When one object
begins to vibrate and it's in touch with another one, and it causes it to vibrate at the same frequency as the first object. Okay. Now the second one is a little bit different because every object has a natural frequency that it wants to vibrate at. Okay. And so basically, if another object starts vibrating at an object's natural frequency, when those vibrates hit it, it will start to vibrate also, and they will kind of feed on each other, make both of them vibrate at a higher frequency. Okay, and so, for example, when we hit one fork of a tuning fork, we don't hit both of the forks. We only hit one of the forks. Well, as it starts to vibrate, it sends vibrations toward this one, and since that is the same frequency that this fork of the tuning fork or tine wants to vibrate at, it begins to vibrate also. And they kind of reinforce each other and increase the vibration. That's one reason why tuning forks are used, because they give a good vibration and they reinforce each other and get it louder and louder, okay? And when you do that, that's called resonance, okay? Re means again, sonance, son, like sonic again, that's the same word, means sound. So basically it means to resound. In other words, the vibrations of one reinforces the vibrations of the other. It makes it vibrate more. We call those sympathetic vibrations. Now, these vibrations, besides being the same object like this, can also do it to opposite objects. We've all seen commercials where a lady sings really loud, and all of a sudden you have this wine glass, and it starts to vibrate and finally to shatter. And what's happening is not so much the volume, although you do have to it makes it easier for a higher volume, but you have to hit the right note. You have to hit the right frequency that will vibrate at the same, so your sound, your voice is vibrating at the same frequency as the natural frequency of this glass. And when those vibrations hit the glass will start to vibrate, and they start feeding on each other, and so it vibrates more and more. And glass is a semi-solid liquid. It can take a little bit of that, but eventually it's vibrating more than it can, and it will shatter. Okay, and that's basically what it has to do with resonance. There are some examples. I'll have some videos perhaps posted where you can look at examples of people doing that. There was a bridge, suspension bridge, big for cars and everything else. That big old sports and everything like this coming down in Tacoma, Washington, in the 1950s. And the wind began to blow, and it was blowing at the same frequency at the bridge as the bridge's natural frequency. And so the bridge continued to swing greater and greater amounts, and eventually just completely collapsed. Fortunately, everybody was able to get out off the bridge, but there were some cars and stuff that were destroyed. They couldn't get out. In the British Army, they had soldiers marching across a bridge in step. Well, in step means they're going to all hit the bridge at the same time with their left foot, hit the bridge at the same time with their right foot, and so on. And if this is at the same frequency as the bridge, then it causes the bridge to vibrate. And once again, if they're in resonance, same natural frequency of the bridge as the frequency of the people marching on it, then they start enforcing each other, and eventually the bridge actually collapsed because of the resonance between the marchers and the bridge wanted to shake at. And so after this, they would break step, which means they just, when we get to a bridge, instead of keeping everybody in step, marching at the same time, they said, well, everybody just kind of march at your own rate until we get to the other side so that we don't have the bridge collapse on us, which is probably a good thing, especially if you're one of the soldiers. All right, now the next topic, and we're not going to talk a lot about it right now because we're about out of time, but is interference. Okay, anytime you have waves that overlap or occur in the same place, they can interfere with each other. All right, and so, for example, let's just look at some water waves here on the right. There we go. Okay, and you have two ripples. When you hit two drops at the same time, they send out these ripples. Okay, well, as the ripples spread into each other, they interfere with each other. All right, now, when they are in phase with each other, in other words, say they're both hitting the top of the wave at the same time, then it makes an even little bigger wave. Okay, but in between that, you see a little shady there is kind of, there's not much. That's where they're out of phase. One's going up, one's going down, and they cancel each other out. Where they
are on top of each other is constructive if they make it bigger, and destructive if they make it smaller.